The next step in our study of electric circuits is to talk about electric current. I'd like to start with a little bit of context and history. Not that you'll get asked about these types of things on a test or anything like that, but I think it's really important to understand we'd already established that static electricity has been observed for thousands of years, but it wasn't really until the European Age of Enlightenment, pre-industrial revolution, but still pretty late in history, that people had a way to scientifically study what was happening with electricity. So in 1650, with the development of the first machine to generate static electricity, this is about the same time that Robert Hooke was discovering the cell, and Isaac Newton would have been a boy, actually, at this time. The next major step was probably about 100 years later with the invention of the Leyden jar, and I'll talk a little bit more about what that is and why it matters in the coming slides. But things started picking up a little bit after that. For example, Benjamin Franklin had the often misunderstood but very famous experiment where he flew a kite in a rainstorm and did that to demonstrate that lightning is the same thing as static electricity, just on a much, much larger scale. And shortly after that, by the late 18th century, we had people making discoveries about electricity connected to the human body. So the scientist Luigi Galvani had an experiment where I believe what he had done was dissected some frogs and had the frog legs hung up in order to perform experiments on them. He was drawing them out and accidentally contacted two ends of the leg with two different metals and saw that the muscles twitched, even though the frog was clearly dead and dissected. From this, he made some really incorrect conclusions, something about the muscles storing electrical energy and believing that maybe that's how static electricity worked. And that was improved upon a lot by people shortly after Galvani. So for example, Alessandro Volta, who discovered that you could replace the frog leg in that experiment with something that was not alive at all. And we'll talk about how that works too. The Leyden jar is a device that is named after the city where it was invented. And it's a capacitor, but that was at a time when we didn't have circuits, so we didn't have capacitors. So they didn't call it that at the time. That's what it is, though. Glass forms a dielectric in this scenario between two pieces of metal. And what this basically was two metal cups with a piece of glass between them. And it was accidentally discovered to store electric charge. Benjamin Franklin is actually the one who made the version that we see here on the right side of this slide. And he did that to test whether the electric charge was stored in one of the metal cups or in the glass or in the water itself. Alessandro Volta's attempts to reproduce Galvani's experiment and then improve upon it led him to try replacing the frog legs with a stack of two different metals, separated by fabric that had been soaked in acid. So as it shows here, if you have copper and zinc separated by some kind of paper or cloth that's been soaked in acid, you get a chemical reaction. You get oxidation and reduction. Each cell of dissimilar metals causing this oxidation and reduction reaction is what generates the potential difference between the two terminals, the positive and negative terminals of a cell. So the chemical reaction occurs until it can't occur anymore, and that's when the cell is declared to be dead. You might be looking at this and thinking, well, it's a battery. Why does he keep calling it a cell? And technically, in order for it to be a battery, it has to be multiple cells working together. I won't be too much of a stickler about that, but I'll try to say cell when I mean cell. And if you call it a battery, I'll understand. We have a lot of different sources of electric power that we use these days, and some of them are direct current, and that's what we're focusing on right now. So like these cells down here in the bottom left corner. But a lot of them are alternating current. And the basic idea for alternating current is that if you have some sort of motion, for example, due to the wind turning a turbine or due to a waterfall creating a turbine, you can generate electricity out of that. There's also solar power, which we will get a chance a little bit to talk about later in the semester. But the idea that each of these different ways of generating electric power are all powering circuits is important because circuits themselves are going to be analyzed following a few simple rules that don't really depend on where that voltage source really is coming from. I'd like to remind you that in some solid materials, at least the ones that are good conductors, electrons can leave their orbitals and move from atom to atom pretty freely in random directions. So for example, in a metallic bond, which we often refer to as a sea of electrons, the reason it's referred to that way is because the outermost electrons in each atom are not really bound to their original nuclei, and they can just move around in random directions. If a potential difference exists in the region of the material, the movement of these electrons from one place to another will generally be in one particular direction, because electrons will move toward a higher voltage. When we analyze circuits, it works just as well for us to think about the holes left behind by the electrons. Rather than discussing the direction that the electrons move, we'll discuss the direction that the holes move. Holes will always move from higher voltage to lower voltage. Electric current is defined as the rate of motion of charge through a cross-section or a point in a wire. The variable for electric current is capital I. A lot of times people use lowercase I because capital I looks a lot like lowercase l or number 1, and that's usually not much of a problem. Capital I is equal to delta Q over delta T through a point, meaning the amount of charge that passes through a point per second. And the unit for current is ampere, where 1 ampere is defined as 1 coulomb per 1 second. An example of how we would use this equation is if, say, 5 times 10 to the 20th electrons flow past a given point in a wire in 10.0 minutes. What is the current through the wire? So the first question would be, what is delta Q in this question? And delta Q is the amount of charge that is flowing past a given point in the wire. 5 times 10 to the 20th electrons is the number of electrons. That's not the charge. The charge is going to be measured in coulombs. Conveniently, we know the amount of charge on each electron, so we can say that 5 times 10 to the 20th electrons are flowing past, where each electron has a charge of 1.6 times 10 to the minus 19th coulombs, for a total of 80 coulombs flowing through this point or past this point in the wire. The next question is, what is delta T? Delta T was given as 10.0 minutes, but you know that you want that in seconds in order to use it in an equation, so we need to convert 10 minutes into seconds. That's pretty straightforward. It's 600 seconds. Now that I know the values for delta Q and delta T, I can put them into the equation where the current is equal to delta Q over delta T, so 80 coulombs divided by 600 seconds for a current or a rate of 0.13 amperes. I want to emphasize that's a lot of electrons for something on the scale of less than 1 ampere. So when we talk about an ampere, we are talking about a lot of individual particles flowing past a point per second. And we'll talk more about that flow of charge in the next few videos.